The world of knowledge is always deeper and more complex than it first appears. We will catch you next time. Usually, when we talk about some massive technological breakthrough, there's this expectation of, absolute precision.
Right. Yeah, like engineering.
Exactly, like engineering. You write a piece of code to, I don't know, calculate a trajectory, and the math just executes perfectly. You can point to the result and say, there it is, it worked exactly as programmed.
It's clean. It's totally predictable.
Right. But uh, step into the world of modern artificial intelligence, and that precision just instantly gives way to this bizarre, almost maddening paradox.
Oh, absolutely. It's a wildly muddy diagnostic scenario right now.
I mean, we live in a world where AI can effortlessly recognize millions of images, right? It can beat human grandmasters at a complex game like Go, and it can predict your next online purchase with this terrifying accuracy.
Yeah, but then that exact same supposedly intelligent system is utterly baffled by, like, a sarcastic comment.
Yes, or a slightly humorous news headline.
hmm
It can navigate a complex video game, but it can't tell you why a joke is funny.
And that's because we conflate output with comprehension. We assume that because a system performs computationally complex tasks flawlessly, it must inherently understand the simple things.
We project our own minds onto it.
Exactly. When an algorithm defeats a grandmaster at Go, we just project human intelligence onto it. We assume it grasps the underlying strategy or the flow of the game, or even the psychology of its opponent.
Hmm. But it doesn't.
It really doesn't.
So today we are taking a deep dive into the absolute bedrock of machine learning to figure out why this paradox actually exists.
And we're going strictly off Chapter 11 from our source material today, Machine Learning and Big Data.
Right. Our mission for this deep dive is to look under the hood of modern AI, strip away all that Silicon Valley marketing hype, and really examine the philosophical and mathematical limitations of how these systems operate.
We're diving into the mechanics of what is formerly known as automated induction.
Yeah, and we're going to understand why feeding an infinite amount of data into a machine does not, and mathematically cannot, equal creating a mind.
It's going to get intensely academic, but in a good way. We're tackling the empirical constraint, the frequency assumption, model saturation.
All the heavy hitters. So to ground this, where do we actually start? I mean, we have to rigorously define what machine learning is, right? Stripping away the sci-fi terminology.
Right, yeah. A highly effective framework for this was established back in 1997 by the computer scientist Tom Mitchell.
Oh, okay. 1997, so this isn't exactly new.
Not at all. He proposed a very clean operational definition. Basically, a computer program is said to learn from experience, which we'll call E.
Okay, experience E.
Right, with respect to some class of tasks, T, and a performance measure, P.
Got it.
So it learns if its performance at tasks in T, as measured by P, improves with experience E.
Okay, let's translate that out of the algebraic notation for everyone listening, and for me, honestly.
Yeah.
So if the task, T, is recognizing a stop sign.
Yep.
The performance measure, P, is the percentage of stop signs it correctly identifies. And the experience, E, is the data set of images that has been shown. So the machine is learning if feeding it more images increases its accuracy.
You nailed it. But the word experience does a ton of heavy lifting there.
How so?
Well, for a human, experience is multisensory, it's temporal, it's deeply contextual. For a machine, experience is just a static data set.
It's just historical data.
Right. Which brings us to the philosophical root of the entire field. Because a machine's experience is exclusively composed of past data, machine learning is simply automated induction.
Automated induction. Okay, let's break that down. Inductive reasoning as a philosophical concept involves inferring general rules from specific historical observations, right?
Exactly. The classic philosophical example is the swan problem.
Oh, David Hume's thing.
Yep, David Hume.
Mm.
If you observe 1,000 white swans, inductive reasoning leads you to the general rule that all swans must be white.
It's a probabilistic guess based on historical frequency.
Right. But the inherent flaw in induction, which Hume pointed out centuries ago, is that you can never be absolutely certain.
Because the 1,001st swan might be black?
Exactly. The future might not actually resemble the past. And because machine learning is fundamentally just automated induction running on silicon, it inherits every single historical and philosophical limitation of inductive reasoning.
Wow. So we are dealing with an ancient philosophical problem running on incredibly fast hardware. It's not some brand new form of cognition.
No, not at all. And to understand how this automated induction is applied, we have to look at the architecture of the field. Machine learning is often described as a big tent containing three main approaches.
Right, I've heard this. Unsupervised learning, semi-supervised learning, and supervised learning.
Yeah. But for this deep dive, and based on the chapter, we are focusing our lens almost entirely on supervised learning.
Why is that? Why not unsupervised?
Well, unsupervised learning, where you just, dump raw data into an algorithm and hope it finds useful patterns on its own, it still lags significantly behind because it lacks human direction.
It lacks the signal.
Exactly. Supervised learning is the engine driving almost all the major AI successes we see today. It's the absolute best case scenario for the technology right now.
Okay, so the defining characteristic of supervised learning is human intervention. The initial input data is meticulously labeled by humans to indicate the desired output, right?
Right. The machine is not discovering the categories. Humans are defining the categories, and the machine is just finding the mathematical correlations that map the raw data to those human-defined labels.
And the most foundational application of this is classification.
Yeah, classification.
Let's unpack the mechanics of that because, like we said, it's not magic, it's statistics.
Sure.
Consider something as ubiquitous as a spam filter.
Oh, perfect example.
That's binary classification.
Right.
The output is a simple yes or no. The algorithm, I think the book mentions the naive Bayes classifier,
Right.
doesn't actually know what spam is conceptually.
No, it has no idea. It doesn't understand the concept of a scam or a marketing email or, a Nigerian prince.
Right. It operates purely on probability theory.
Exactly. A naive Bayes algorithm basically calculates the conditional probability of an email being spam given the presence of certain words. It looks at the human-supplied hints.
You mean the labels? Like the thousands of times users have manually clicked mark as spam?
Yes. It analyzes the frequency of specific words in those labeled emails. So if the words, say, Viagra or urgent, appears in the spam folder at a vastly higher frequency than in the normal inbox, the algorithm adjusts its internal weights.
Why is it called naive, though?
The naive part of naive Bayes is the mathematical assumption that every feature, every single word is independent of the others.
Which isn't how human language works at all.
Right, not even a little bit.
Yeah.
But it is computationally very efficient. The system assigns a numerical score to incoming text based purely on those past historical frequencies.
So it's just a mathematical feedback loop converging on a boundary line between acceptable text and junk.
Precisely. But binary classification is just the shallow end of the pool. To see the true scale of supervised learning, we have to look at massive scale classification.
Like the ImageNet project.
Yes, ImageNet is the perfect example. They didn't just want a yes or no. They wanted to classify millions of images into thousands of highly specific categories.
And to do this, researchers scraped an astronomical number of raw images from the internet. But raw pixels are useless to a supervised learning algorithm without a target, right?
Exactly. So they utilized Amazon's Mechanical Turk platform.
Oh man, this is wild. They paid a sprawling army of human workers micropennies to manually look at these images and literally draw bounding boxes around objects.
The scale of human labor required to make the machine appear intelligent is just staggering. Those human workers mapped the raw pixels to a vast lexical database called WordNet.
Which organizes English words into a strict ontological structure, right?
Yeah. The human workers provide the ground truth. They told the system, hey, these specific clusters of pixels represent a dog. These represent a piano. These represent a hussar monkey.
A SAR monkey.
Yeah, a very specific type of monkey. The machine learning model, which is usually a convolutional neural network, then processes the raw pixel data.
And to the computer, that data is just a massive grid of numbers representing red, green, and blue intensity values.
Exactly. Through iterative training passes, the network adjusts millions of its internal parameters until the mathematical output of its processing matches the human-provided label of hussar monkey.
So the machine is definitely not learning what a monkey is.
No, it is optimizing a mathematical function to map pixel intensity arrays to a specific text string. That's it.
And that logic extends directly into natural language processing, or NLP, through what the chapter calls sequence classification.
Right. Like when an algorithm automatically tags a news article as politics or sports, it's performing a similar mapping trick.
I remember reading about the early days of this. They used a bag of words model, right?
Yeah, bag of words or BOW.
It literally stripped away all grammar, syntax, sentence structure, and just threw all words in the document into an unstructured mathematical bag.
Yep. And it just counted the frequencies. If ball, stadium, and referee were in the bag, it tagged it sports.
So it didn't matter if the sentence was, the referee threw the ball in the stadium, or the ball referee stadium show in.
Nope. The machine was entirely blind to word order.
Wow. But eventually they moved beyond that, right?
They had to. Moving beyond the bag of words model required introducing ordered text models. These acknowledge that the position of a word matters. For instance, words in a headline or the first paragraph are statistically more indicative of the article's core topic.
But again, this relies on humans having previously annotated massive corpora of text, tagging articles of topics to provide that training signal.
Exactly. And this scales down to the microscopic level with sequential learning, where the goal is to tag individual items within a sequence.
Like part of speech tagging.
Right. You feed the system, the sequence, the brown cow.
Yeah.
We as humans know the grammatical rules of English. We know what an adjective does.
But the machine is completely ignorant of grammatical theory.
Totally ignorant. Instead, it is fed tens of thousands of sentences where human linguists have manually annotated every single word. The is tagged as a determiner, brown as an adjective, cow as a noun.
And then the algorithm processes these sequences and calculates the statistical probability of word orders.
Yes. It learns that a word tagged as an adjective is highly likely to be followed by a word tagged as a noun. It just models the transitional probabilities.
And that exact mathematical architecture, scaled up, is what drives named entity recognition, right? Identifying people, corporations, or locations in text.
It drives that, and it drives time series prediction analyzing sequential data points over time.
So whether it's series voice recognition predicting the next word in a text message, or an AI diagnosing a medical condition from sequential patient data, or even predicting stock market fluctuations.
The underlying mechanism is completely identical. The system relies strictly on inductive inference derived from the statistical patterns found in the labeled historical data it was fed.
You know, it fundamentally reminds me of an analogy. I'm trying to picture this. Is this essentially like a person locked in a room and they're tasked with learning how to cook by only ever tasting finished dishes?
Oh, that's a good way to put it.
Right, like they're handed a slice of cake and a piece of paper that says cake. They're handed a bowl of soup and a piece of paper that says soup. They're expected to eventually reverse engineer the recipe in the cooking process entirely from the final sensory input.
Exactly.
So they know that a specific combination of sweetness and spongy texture corresponds to the label cake. But they have absolutely zero conceptual understanding of what flour actually is.
Right. They don't know that wheat grows in a field.
They don't know the chemical reaction that occurs when baking powder interacts with heat. They don't even understand the physical concept of an oven. They have merely mapped the final output to a label.
That is a very precise summation of the mechanism. The algorithm is mapping the final input, the array of pixels, the vector of words, the sensory taste in your analogy, to the target label. It lacks any internal model of the physics, chemistry, or semantic reality that generated the data.
It operates entirely on correlation, completely devoid of causation or comprehension.
Yes, and if you're listening to this and wondering why this mathematical distinction between correlation and comprehension actually matters to your daily life.
Yeah, why should you, the listener, care?
Because this exact mechanism, the supervised inductive learning algorithm, is the invisible architecture of your entire modern web experience.
It's the engine that personalizes your news feeds, filters your inbox, curates your social media timeline, and recommends what you should buy or watch next.
Exactly. If you linger on an article about a political scandal, the supervised learning algorithm running on the back end doesn't understand the scandal. It doesn't understand politics or ethics or human behavior.
It merely registers a statistical correlation between your user profile and specific lexical features in the text.
And then it aggressively optimizes its output to feed you more text containing those features. It can classify the sentiment of a post as positive or negative and tailor your digital reality based on those classifications, all while being fundamentally blind to meaning.
Which brings us to a crucial conceptual threshold in this deep dive.
Yeah.
Because supervised learning is so incredibly effective at these specific bounded tasks, it creates a really powerful illusion.
A massive illusion. When an algorithm accurately tags a photo or translates a sentence or curates a feed that keeps us engaged, it is dangerously easy for the human mind to assume the machine possesses actual understanding.
We project comprehension where there is only computation.
Right. But machine learning, when analyzed mathematically, is not a process of understanding. It is intrinsically a process of simulation.
The algorithm is the ultimate great pretender.
I like that. Mathematically, the system assumes that there is some hidden underlying pattern governing the real-world phenomenon it's analyzing.
But the algorithm's objective is not to comprehend that hidden pattern. Comprehension would require access to reality outside the dataset.
Right. Instead, its objective is to simulate the hidden pattern by mathematically mimicking its footprints left behind in the data. It attempts to construct a mathematical function, let's call it function, that perfectly replicates the input-output behavior observed in the training set.
Let's examine how this simulation plays out in a complex natural language processing task. The chapter talks about semantic role labeling.
Yes. The goal here is to get the machine to identify the underlying relationship between words in a sentence. Consider the source's example sentence. John threw the ball to Lizzie.
Okay, John threw the ball to Lizzie. The system analyzes the text and correctly outputs the semantic tags. It labels John as the agent, threw as the action, ball as the theme, and Lizzie as the recipient.
Exactly. Now, to a human observer, looking at that flawless output, it seems undeniable that the machine understands what is happening.
Because when a human reads, John threw the ball to Lizzie, an entire universe of contextual understanding instantly activates. You implicitly understand human agency.
You know what a ball feels like, its weight, its texture.
You intuitively grasp the physics of gravity and momentum required for the act of throwing. You understand the spatial relationship and the temporal sequence. First, John has the ball, then the ball travels through the air, then Lizzie has the ball.
The machine possesses absolutely none of that ontology. It has generated function, a highly complex statistical model, to apply those semantic labels based entirely on the probabilistic distribution of word sequences it observed in its training data.
So it recognized the syntactic structure, noun, verb, noun, preposition, noun, and mapped it to the labels it was mathematically rewarded for choosing in the past.
Precisely. It is completely simulating comprehension. It's generating the exact output a human would give using a completely alien, purely mathematical mechanism.
And this reliance on historical simulation introduces a massive vulnerability, doesn't it? What the text calls the time slice problem.
Oh, the time slice problem is huge. A data set, no matter how unimaginably massive it is, no matter how many petabytes of text or exabytes of video it contains, is inherently just a microscopic time slice of the past.
A frozen snapshot.
Yes.
Yeah.
But the actual real world is dynamic. It is generating new data continuously, perpetually evolving, constantly shifting its underlying rules.
And because the machine learning system's entire world is bounded exclusively by the data it was trained on, it is permanently and irreversibly backward-looking.
It learns statistical bell curves of past behavior, not the underlying mechanics of meaning. And this is a catastrophic structural limitation when a system is deployed into a chaotic, dynamic reality.
The simulation is inherently brittle.
Very brittle. The algorithm can predict outcomes with stunning accuracy, maintaining the illusion of deep understanding right up until the moment it encounters a random exogenous event.
An event that exists outside the statistical distribution of its training time slice.
Yeah.
Let me test an analogy here. It sounds like a student who memorized the exact answers to a specific math test. They get 100%. But if you change a single number in the equation, they fail completely because they never learned how to actually multiply. They just learned the pattern of the test.
That's a great way to think about it. The chapter also uses a really good example regarding self-driving cars.
Oh, right. Imagine you train a self-driving car system exclusively using every single photograph and film reel recorded between, say, 1950 and 1959.
Okay, yeah.
You feed it millions of hours of driving data. The system mathematically optimizes its function. It learns the exact contours of 1950s sedans, the shape of the roads, the behavior of pedestrians and fedoras.
It becomes the ultimate master of 1950s driving.
Right. It scores 100% of its training data. Then you drop that exact system into the middle of a modern city today.
It would be a disaster.
It instantly encounters a teenager silently gliding across an intersection on a battery-powered electric unicycle while looking at a smartphone. The AI crashes the car immediately.
Not because it failed to calculate, but because the electric unicycle, the smartphone, the lack of engine noise, none of these variables existed in the 1950s time slice.
The system didn't learn the physics of driving or the concept of caution. It only learned the exact statistical distribution of the 1950s dataset.
That analogy perfectly isolates the failure point. The system's complete lack of causal understanding means it cannot generalize outside its training distribution.
We see this brittleness constantly in personalization algorithms, too. The texts have a great example about this. Let's say a user, Joe, has a history of reading conservative bloggers.
Right. And just to be clear to the listener, we are just analyzing the mechanics here, not endorsing any political viewpoints. The text uses this to illustrate the filter bubble.
Absolutely. Strictly impartial analysis of the source material. So the personalization algorithm analyzes Joe's time slice of historical clicks, maps his profile to a conservative cluster, and begins aggressively filtering his feed to show only conservative content.
It works flawlessly from a mathematical standpoint, maximizing his engagement.
Until the day his friend recommends a brilliant, highly relevant article from a left-leaning magazine. Joe would actually love the article, but the algorithm completely screens it out.
It hides reality from him because its mathematical simulation of Joe is rigid, based entirely on his past behavior.
Or consider another user, Mary, who spends years interacting with content about horses. The algorithm concludes Mary equals horses. Then, tragically, Mary's horse dies.
Oh, that's a sad one, but a perfect example. She goes through a period of intense grief and subsequently develops a deep interest in Zen Buddhism as a coping mechanism.
But the algorithm is entirely oblivious to the human reality of grief, emotional transformation, or evolving interests. It has no mechanism to understand why Mary liked horses, or why she stopped.
It simply observes a sudden drop in engagement with horse content and a spike in Buddhism content. For a period, it will forcefully continue serving her horse-related ads, completely failing to adapt to her new reality until enough new data points are collected to shift the statistical weight of her profile.
This inherent brittleness is the defining characteristic of what we call narrow AI. These systems are incredibly powerful, but completely fragile the moment they step outside their strict, predefined parameters.
Like when Google's DeepMind trained an AI to master a suite of classic Atari games, the headlines were massive.
I remember that. It was hailed as a monumental leap toward general intelligence. The AI figured out strategies humans had never considered.
Yeah, but if you take the system that mastered the Atari game Breakout and you ask it to play a game of Go or chess or even a different Atari game with slightly altered physics, it fails completely.
It cannot transfer its knowledge because it didn't learn the concept of a game or strategy or rules. It just optimized a mathematical pathway for a highly specific pixel environment.
This explains why the field is perpetually stuck on highly specific, narrowly defined applications with virtually no tangible progress toward artificial general intelligence or AGI.
Because, for a biological organism, learning is intrinsically about escaping narrow constraints. Humans learn to extract generalized models of the world that can be applied to entirely novel situations.
Right, if you learn to drive a tractor, you can reasonably infer how to drive a car or even pilot a boat because you understand the generalized concepts of steering, acceleration, and spatial navigation.
But because machine learning systems are purely data-driven statistical simulations, they are conceptually imprisoned by their datasets. They cannot extrapolate meaning, they can only interpolate data.
Exactly. So if the tech industry recognized that the limits of the simulation were entirely defined by the boundaries of the dataset, if the time slice was the inherent problem, the logical engineering solution seemed obvious.
Just make the dataset unimaginably huge.
Yes. If you lack the full picture, capture every single pixel of reality possible. Make the time slice so massive it effectively covers everything.
And this ideological pivot ushered in the massive hype cycle of the big data era.
It's essential to trace the historical evolution of the big data concept to understand how the hype obscured the reality of the technology.
So where did the term actually come from?
The terminology big data first appeared in academic print around 1997, specifically in a NASA paper.
Wait, really? NASA.
Yeah, they were discussing the computational challenges of visualizing massive data sets using computer graphics. It was a technical descriptor, not a paradigm shift. However, it steadily migrated into the realm of business intelligence.
And the turning point was that 2001 report by the Gartner Group, right?
Yes, that's the one.
That's the report that introduced the famous 3Vs framework.
The Gartner report defined the impending data challenge by its volume, the sheer amount of data being generated, its velocity, the speed at which data was moving in and out of systems, and its variety, the range of unstructured data types like text, video, sensor logs.
And as computational power became exponentially cheaper and more available, driven by Moore's law, the ability to store and process these massive data sets became a reality.
And the hype began to compound. By 2014, the frenzy reached its absolute zenith. Forbes magazine published an article titled 12 Big Data Definitions. What's yours? capturing how the term had become this amorphous buzzword applied to everything.
Corporate hierarchies were literally restructured. Companies were inventing entirely new executive roles like vice president of big data.
Yeah. But we shouldn't dismiss the era entirely because there were some massive, undeniable early triumphs that provided the oxygen for all this hype.
True, these weren't just theoretical papers, these were real-world applications generating massive value. A perfect example from the chapter is Oren Etzioni and his startup, Faircast, founded in 2004.
Right. Etzioni didn't build a better aerodynamic model of an airplane. He utilized big data. He secured a data set of nearly 200 billion historical flight price records.
2 billion.
Yeah. By analyzing the historical fluctuations, the volume, velocity, and variety of pricing changes, he built a predictive model that could accurately forecast whether a specific airfare was likely to go up or down in the near future.
It was a purely statistical prediction engine, and it worked so effectively that Microsoft acquired the company in 2008 for over $110 million.
That paradigm of brute force statistical correlation was rapidly replicated across massive industries. Retail giant Walmart established Walmart Labs specifically to apply big data analytics to their global logistics chain.
Oh, right. Analyzing petabytes of consumer transaction data to predict demand spikes and optimize shipping routes before a local trend even fully materialized.
And in municipal infrastructure, researchers from Columbia University utilize big data to tackle a highly unpredictable problem, predicting manhole explosions across Manhattan's grid of 50,000 manholes.
You cannot afford to physically inspect 50,000 manholes daily.
Exactly. By aggregating historical data on cable age, previous incident reports, electrical load, and weather patterns, they constructed a predictive model that flagged high-risk manholes.
The sheer unprecedented scale of the data unlocked capabilities that were fundamentally impossible for human analysts.
But this string of undeniable successes led the tech industry to make a massive and frankly dangerous philosophical leap. And this is where we have to talk about the end of theory myth.
Yes. The most infamous crystallization of this idea came in 2008, when Chris Anderson, the editor-in-chief of Wired magazine, published an article essentially arguing that the era of big data meant the end of the scientific method as we knew it.
The central thesis was that with enough data, the numbers speak for themselves.
The argument was that we no longer needed scientists to formulate hypotheses, build semantic models, or understand the underlying causality of a phenomenon. We just needed to dump petabytes of data into a supercomputer, and the algorithms would find the correlations, and those correlations would be enough.
It was a monumental conceptual error, and it requires rigorous deconstruction. The end of theory argument is a profound logical fallacy.
Why? Because data sets, regardless of whether they are measured in gigabytes or yottabytes, are fundamentally inert.
Exactly. They are historical records. They are numbers sitting on a hard drive. Data cannot think, it cannot interpret itself, it cannot generate a hypothesis, and it cannot extract meaning. The tech industry mistakenly credited the data itself for the breakthroughs.
So to use an analogy, we essentially confused the fuel for the engine. We are digging up these massive, unprecedented reserves of high-octane gasoline, pouring it into our cars, and when the cars went faster, we declared that the gasoline was magical.
That's a great analogy.
We completely ignored the fact that over the last decade, we had fundamentally redesigned and upgraded the engine itself.
Precisely. The true hero, the actual driver of the breakthroughs during the big data era, was the quiet, relentless advancement of machine learning algorithms, specifically the maturation of deep learning neural networks, combined with the raw computational horsepower provided by modern GPUs.
It was the statistical techniques, the complex math, that was doing the heavy lifting of extracting the patterns. The data was simply the prerequisite fuel.
Without the advanced engine of the algorithms, big data is just digital hoarding. Today, the term big data has largely receded as an independent buzzword. It's now simply acknowledged as big data AI, a necessary environmental condition for training models, but unequivocally not the source of intelligence itself.
Okay, let's follow that logic to its natural conclusion. If the massive data sets are just the fuel, and the sophisticated machine learning algorithms are the highly engineered engine, what exactly is the structural barrier preventing us from driving this vehicle all the way to artificial general intelligence?
We have optimized the engine, we have an infinite supply of fuel.
Right. Why are we still hitting a wall? This brings us to the first major, mathematically insurmountable roadblock outlined in the chapter, the empirical constraint.
To deeply understand the empirical constraint, we have to examine the granular reality of how AI scientists prepare data for an algorithm. They rely on a process known as feature extraction.
Feature extraction. Okay.
An algorithm cannot just look at raw data and understand it. Scientists must define and identify specific syntactic features, essentially pieces of evidence within the dataset that help the algorithm home in on the desired output.
Let me make sure I have this straight. If I am training an algorithm to identify a horse in a photograph, the raw data is just millions of pixels. A feature might be the specific geometric curve of a horse's ear or the unique color gradient of its snout, represented as a mathematical array of pixel intensities.
Exactly. The algorithm learns to weight those specific features mathematically. But here is the absolute non-negotiable empirical constraint that limits the entire field. These features must be capable of being extracted purely computationally.
Purely computationally.
Meaning what?
They must be mathematically definable and automatically extractable by a computer program without any human intervention. This has to hold true not just during the controlled training phase, but crucially during the autonomous production phase when the AI is deployed in the wild. You cannot have a human sitting in a server farm manually drawing a red arrow in Photoshop on every new incoming image saying, look at this specific part, this is the ear.
Right. The machine must isolate the feature using syntax alone.
And that purely computational requirement, being fundamentally trapped in the realm of syntax without access to semantics, creates massive, unresolvable blind spots.
Yes, it does. Let's walk step by step through a concrete case study from the text to show how this breaks down.
Yeah.
The blue box ink problem.
Okay, let's hear it.
Let's say a major corporation named Blue Box Inc. hires a tech firm to build a named entity recognition AI. The goal is to monitor social media and flag every single post, tweet, or article that mentions their company.
Seems simple enough, but the engineers are bound by the empirical constraint. We have to design syntactic features that the machine can extract purely computationally from a stream of text.
Right. So what are the allowable computationally extractable features? They can use orthographic features, instructing the machine to check for the capitalization of the letters B and B.
Or they can use lexical features, checking for the string of characters blue, immediately followed by the string box.
Exactly. They can check if those strings are in close proximity to the acronym INC, or they can rely on a previously trained part-of-speech tagger to identify if the phrase is functioning as a proper noun in the sentence structure.
All of these are purely syntactic rules based on the shape and arrangement of the characters. Okay, that sounds like a solid set of rules. Where does the empirical constraint cause it to fail?
It fails spectacularly the moment it encounters the complexity of human reference, specifically what linguists call the co-reference resolution problem.
Co-reference resolution.
Imagine the AI scans a financial blog post that reads, Blue Box had a phenomenal first quarter. The company's profit margins soared by 20%.
To a human reader, it is instantly and inherently obvious that the phrase, the companies, refers directly back to Blue Box.
But the AI is trapped in syntax. It scans the second sentence. It does not see a capitalized B. It does not see the lexical string Blue Box.
It cannot use the phrase, the companies, as a syntactic feature to trigger a flag unless it can purely computationally mathematically link it back to the previous sentence.
And co-reference resolution, teaching a machine to understand that pronouns or descriptive nouns point back to previously mentioned entities, is a notoriously difficult unsolved problem in NLP, precisely because it often requires semantic understanding, not just syntactic matching.
But wait, if it's just matching syntax, what happens when we introduce outside context?
Uh-huh.
What if a tech historian posts an anecdote on a forum and they write, the eccentric founder of XYZ Corporation loved the color blue, and he wanted a simple interface, so he named the prototype operating system Blue Box.
Oh, that's where it really falls apart. As a human reading that sentence, you use your real-world knowledge of how corporations name products versus how they name themselves.
Right. I know instantly that Blue Box in this context is a piece of software, not the corporation Blue Box, Inc.
But the AI system is completely blind to that context. It scans the text, finds the capitalized B, finds the lexical string Blue Box, and flags it as a match.
It generates a false positive because it cannot extract contextual world knowledge purely by looking at the syntax of the input string.
That is the core of the issue. The AI is structurally forbidden from accessing anything outside the dataset. It is locked in a room, entirely blind to the meaning of the words, only permitted to analyze the physical shapes of the letters and the spaces between them.
This proves definitively that data alone, regardless of its volume or velocity, cannot overcome the empirical constraint. A truly intelligent system requires evidence in a much broader semantic sense. It requires context, logic, and an understanding of the real world.
And the empirical constraint strictly forbids the algorithm from accessing anything other than computationally processed syntax.
This is maddening. As a human, I just read it and I know.
Got it.
But okay, so since the algorithm is permanently locked in this room, only allowed to look at syntax, how does it actually decide which of those allowable features are important? If it doesn't know what a company is, how does it learn that the shape of the letters I and C means it should flag the post?
It has to count them. And this reliance on counting introduces the second major roadblock, the frequency assumption.
The frequency assumption.
The frequency assumption is the direct, inescapable consequence of relying on enumerative induction. For a machine learning system, more is always better.
At their absolute core, beneath all the marketing and complex algebra, these systems are simply incredibly sophisticated high-speed counting machines.
If the string of characters ink follows a pair of capitalized words 5 million times in the training data, and the human annotators have labeled those instances as company, the learning algorithm mathematically attaches an overwhelmingly high probability weight to ink as a definitive feature of a company.
It learns by counting co-occurrences.
It's a statistical brute force approach. Patterns that are completely undetectable in a sample of 100 examples become mathematically crystalline when you have 1 billion examples.
And we should acknowledge that this counting mechanism powers highly effective and necessary technologies. It is the fundamental mathematics behind anomaly detection.
Right, like if a bank wants to detect fraudulent credit card transactions or a cybersecurity firm wants to detect improper employee logins.
The machine learning system analyzes billions of historically normal events. By establishing a massive, dense statistical cluster of what we can call a normality assumption, the rare events, the anomalies, stick out mathematically as outliers on the distribution curve.
The system doesn't know why a login from Russia at 3 a.m. is bad. It just knows it is statistically infrequent compared to the historical cluster of 9 a.m. logins from Chicago.
And that exact same counting mechanism is also what constructs the personalized filter bubbles we discussed earlier. By relentlessly counting your clicks, the system maps your statistical cluster.
If you click on 3 left-wing news articles, it serves up a fourth, counting on the frequency of your past behavior to predict your future engagement.
It creates radicalized echo chambers not out of malice, but based purely on repetitive syntax counting and engagement optimization. But here is where the frequency assumption hits a catastrophic conceptual brick wall.
The fatal flaw of relying entirely on counting is that it fundamentally destroys nuance. Specifically, the frequency assumption annihilates things like sarcasm, irony, and humor.
Because those forms of communication are inherently infrequent, and they rely entirely on non-literal semantic meaning.
Sarcasm is an absolute nightmare for machine learning algorithms. Tech companies desperately want to solve this. Google would love to computationally detect sarcasm so they can serve more accurate targeted ads.
But consider a scenario where a user is snowed in during a massive blizzard in January, and they sarcastically post on social media, "Oh, great, another blizzard. Someone get me some sunscreen."
A purely syntax-driven, context-blind ad system analyzes the text. It identifies the high-frequency feature, sunscreen.
It literally serves that freezing user advertisements for SPF 50 sunblock instead of battery-heated socks or snow shovels.
Sarcasm is not a syntactic feature that can be extracted computationally. Furthermore, literal statements vastly outnumber sarcastic statements in any general dataset.
Therefore, the frequency assumption dictates that the algorithm will almost always default to the literal interpretation, completely missing the inverted intent of the user.
To see how this breaks down in the real world, we can look at how text classification AI handles actual news stories. The chapter provides 2 incredible examples involving Associated Press stories that perfectly illustrate this death of sarcasm by frequency.
Oh, I loved this part. The first is a story that ran on Yahoo News with the headline, "Your Tacos or Your Life."
Yeah, that headline alone is gold.
Right. I'll paraphrase the details, but it's essentially about a 35-year-old man in Fontana, California. He buys $20 worth of carnitas tacos from a street vendor. He is riding his bicycle home when a suspect confronts him, punches him in the face, pulls out a handgun, and robs him specifically of his bag of tacos.
Now analyze how a purely syntax-driven text classifier processes that article. It strips away the narrative, it performs feature extraction, it counts the frequencies of specific lexical features.
It sees the word suspect, it sees victim, it sees flee, and it sees handgun.
Based on the massive corpus of news data it was trained on, these specific features appear at an overwhelmingly high frequency in stories related to violent crime.
Therefore, the frequency assumption dictates that the algorithm will flag and categorize this unequivocally as a standard violent crime report.
But as a human, the moment we read the opening line of the AP story, which was something like, "A hunger for carnitas nearly led to some carnage," we instantly recognize the journalist's intent.
We know it is humorous. It is funny precisely because of the absurd disproportion of the event. Someone committed a felony armed robbery for $20 worth of tacos.
But frequency kills humor. The AI defaults to counting the statistical weight of the word handgun and completely fundamentally misses the human intent and the comedic absurdity behind the text.
The second Associated Press story is an even starker example of this limitation. The headline reads, "Boy, 11, bites pit bull to fend off attack."
The incident occurred in Belo Horizonte, Brazil. An 11-year-old boy named Gabriel Almeida is playing in his yard when a pit bull named Tita attacks him.
The dog bites the boy's arm. In a desperate act of self-defense, the boy grabs the dog by the neck and bites the dog back so viciously that the boy actually loses one of his own canine teeth in the struggle.
The boy later gives a quote to the local newspaper saying, "It is better to lose a tooth than one's life."
It is an absolutely incredible quote and a wild story. But once again, when you run this through a machine learning text classifier, it completely fails to grasp the uniqueness of the event.
It extracts the features, boy, pit bull, attack, bite. It compares those frequencies against its historical database, and it categorizes the article as a standard, tragic dog attack story.
Philosophically, this exposes the core deficit of automated induction. Humans immediately recognize that the highly unlikely, completely inverted nature of these events, an armed robbery for street food, a child biting a dangerous dog, is the exact reason they are newsworthy.
The rarity, the deviation from the norm, is the entire point of the communication, but the AI acts as an idiot savant. It is mathematically chained to the frequency assumption.
It defaults to the highest probability bell curve.
It completely misses the point of the story because it has no capacity to contextualize a rare abnormal event against the broader unstated backdrop of human norms. It cannot understand that the exception is the story.
It is funny to imagine a supercomputer earnestly categorizing a taco robbery as a mod hit, but, the real-world implications of this are profound and slightly terrifying.
Oh, absolutely.
If we are increasingly trusting these opaque, mathematically driven systems to curate our reality, to filter our news consumption, to categorize human behavior in security or legal contexts, but they fundamentally cannot understand intent, irony, or the significance of a rare event, because those things don't happen often enough to form a statistical bell curve.
What critical parts of the human experience are we losing in translation?
We are losing the fundamental core of human communication. We are relying on systems that reduce complex intentional language to mere syntax, entirely stripped of the human intent that generated it. And the most sobering realization for the tech industry is that there are no known architectural fixes for this within the current paradigm of purely inductive machine learning.
Right. The empirical constraint and the frequency assumption are permanent fixtures of the math. Pursuing artificial general intelligence through these specific methods is a mathematically proven dead end.
Let me push back on that for a second, because the tech industry's counterargument is always scale.
Naturally.
We acknowledge that the AI is trapped by syntax, and we acknowledge it is constrained by frequency. But what if we just keep scaling the compute power? Look at modern large language models. If we collect an essentially infinite amount of data, every book ever written, every forum post, every line of code, and we run it through massive neural networks, don't we see emergent properties?
I hear this argument constantly.
Can't we eventually overcome these hurdles purely through brute force scaling?
The mathematical reality is no, we cannot. And the reason is our third major roadblock outlined in the text: model saturation.
Model saturation.
Saturation is a rigorously defined mathematical threshold. It is the point at which adding more training data, or more examples, to a learning algorithm completely ceases to yield any meaningful boost in its predictive performance.
It hits a ceiling.
It hits a hard mathematical ceiling. Training cannot go on ad infinitum, returning higher and higher accuracy.
So a saturated model is effectively finished. Adding a billion more parameters or a trillion more tokens doesn't change its fundamental capability.
Exactly. The learning curve flattens out entirely, and this is not a fringe theory advanced by critics. It is an acknowledged reality within the highest echelons of AI research.
The book cites Peter Norvig, right?
Yes. Peter Norvig, the former director of research at Google, a pioneer in the field. Back in 2013, long before the current generative AI boom, he issued a stark warning about the diminishing returns of massive datasets.
He asked the fundamental question, as we gain more data, how much better does our system get?
And his definitive answer is that we are rapidly approaching the point where we get significantly less benefit from new data than we did in the past. The models saturate.
We can observe the real-world consequences of this saturation everywhere today, despite the marketing hype. Look back at those ImageNet classification competitions we discussed earlier.
The models are currently sitting at around 98% accuracy for their top 5 predictions. If you spend millions of dollars to collect, label, and process another billion photos of a hussar monkey, you might push that accuracy to 98.1%.
The model has mathematically saturated on the task of object classification based on pixel geometry. It will never achieve 100% because it lacks semantic understanding of what an object actually is, and more data cannot bridge that specific gap.
And the most glaring multi-billion-dollar example of model saturation is the self-driving car industry. A decade ago, we were confidently promised that fully autonomous Level 5 self-driving cars were just months away.
But today, they remain largely trapped in a heavy, highly controlled research and development phase, restricted to map geofences in specific cities.
Why? Because the machine learning models saturated on normal driving data years ago. They have millions of hours of data on highway cruising, yielding to stop signs, and staying in a lane.
They have mastered the center of the bell curve.
But they are failing catastrophically on the infinite long tail of atypical, dangerous, and chaotic driving scenarios.
The weird stuff. The unpredictable human element. A couch falling off a truck on the highway, a pedestrian wearing a bizarre costume, a construction zone with conflicting temporary signage.
Yes, the models saturate on the normal, frequent events, but they mathematically cannot generalize to the abnormal, infrequent events because they lack a conceptual understanding of the physical world.
They don't understand the physics of a falling couch. They just see an anomalous cluster of pixels that doesn't match their training distribution.
Scaling up the data set to include one instance of a falling couch doesn't solve the problem because the universe of potential abnormal events is infinite.
The assumption that systems can scale indefinitely from narrow initial successes to full-blown general intelligence simply by adding more compute and data is mathematically naive.
Interpolation predicting a point within your dataset scales. Extrapolation predicting a point outside your dataset requires understanding. Deep learning is a powerful tool for interpolation, but it is not a silver bullet for intelligence.
Which brings us to a profound philosophical wrap-up. To understand why we are stuck, we actually have to go all the way back to 1950, to the very foundation of computer science, and look at Alan Turing.
Turing is rightfully considered the godfather of this entire field. In his seminal papers, he hoped that computers could eventually be made to learn things that they weren't explicitly manually programmed to know.
He theorized they might achieve this through a process he called scientific induction.
But this reveals a critical historical divergence, and it raises a fundamental question about how science and human cognition actually work. Turing, despite his sheer genius in mathematics and cryptography, fundamentally misunderstood the broader scientific method.
Real scientists, when making breakthroughs, do not rely purely on induction. They do not just sit there passively counting observations, logging data points into a spreadsheet until a unified theory magically materializes from the math.
Right. Johannes Kepler didn't just stare at a million data points of planetary positions and mathematically average them out.
He made a conceptual leap. He hypothesized that the orbits were elliptical, not circular, which fundamentally changed how the data was interpreted.
Exactly. The process Kepler used, and the process humans use daily, relies on what the philosopher Charles Sanders Peirce defined as abductive inference.
Abductive inference, that's entirely distinct from induction.
It is. Abductive inference involves making conceptual leaps of logic. It is the process of forming an explanatory hypothesis. Scientists make educated guesses, they construct abstract models of reality, they test those models against the data, they understand the broader context, and they revise their theories.
Crucially, they bring intelligence to the analysis of the data as a prior, necessary step. The intelligence precedes the data analysis. It is not merely an emergent byproduct of counting the data.
So, Because modern machine learning is entirely, unapologetically, and purely inductive, because it is, at its core, just a highly sophisticated statistical counting machine locked in a room, permitted only to analyze syntax, it completely lacks this fundamental human spark of abductive inference.
It cannot guess. It cannot form an original hypothesis. It cannot leap beyond the boundaries of its historical time slice.
And therefore we must conclude that we are still fundamentally in search of Turing's true learning machines. The empirical constraint chaining the system to pure syntax and the frequency assumption chaining the system to past probabilities are not temporary engineering hurdles.
They are permanent mathematical roadblocks for any purely inductive system.
Induction alone, no matter how massively scaled, is simply not enough to achieve general intelligence.
So despite all the billions of dollars of venture capital, despite the breathless magazine covers and the endless hype cycles, and despite the very real, highly profitable conveniences these narrow systems provide in our daily lives, we haven't actually built an artificial mind.
We built the world's most complex, incredibly fast abacus, and we mistakenly looked at it and thought it was a brain.
That is the precise, unvarnished reality of the technology today. This has been an absolutely fascinating breakdown. Thank you for walking through the deep math and philosophy of this with me.
Oh, my pleasure. It's a topic that definitely needs more rigorous analysis out there.
And thank you, listening, for sticking with us on this intensely detailed deep dive. We promised at the top of the show that we wouldn't just skim the surface, and I hope we delivered on giving you the intellectual tools to dismantle some of that ubiquitous AI hype. But before we wrap up today, I want to leave you with a final, slightly provocative thought to mull over.
Oh, I'm ready.
We started this entire conversation talking about the expectation of precision, the clean binary X-ray of traditional software. But now you know the mechanics. You know that the AI systems silently curating your world are actually dealing in murky, backward-looking probabilities, not precision. So the next time you open up a streaming service or an online retailer or your favorite social media feed and you see a hyper-personalized recommendation staring back at you, take a moment to realize what you are actually looking at.
Yeah, that's a chilling thought.
You are not interacting with a digital mind that truly knows you. You are looking into a purely mathematical rearview mirror. You are interacting with a system structurally trapped by syntax, blindly counting the frequency of your past actions, completely and utterly unaware of your uniquely human capacity to change your mind, to suddenly understand a joke, or to imagine a future that hasn't even happened yet. The question we have to ask ourselves as we integrate this technology deeper into our lives is this: how much of our rich, unpredictable, uniquely human experience